Autonomous navigation in cluttered and highly dynamic environments still remains a challenge in the domain of UAV research. In this paper, we present a novel end-to-end learning-based approach to control the quadrotor to avoid dynamic obstacles while flying through cluttered environments. We firstly use an encoder to compress the massive point cloud data from the lidar into a single-dimension array which presents the obstacle outline, and then stack multiple historical arrays into a two-dimension obstacle map which contains the kinematics of the surrounding dynamic obstacles. We trained a neural network consist of a residual image encoder and a multi-layer perstoppant, which could give acceleration command to the low-leveled flight controller, according to the observed obstacle map and the quadrotor's current state. The network was trained by Unity ML Agents Toolkit. We set up for parallel agents in the training environment and trained it at 5 times speed. In order to evaluate the performance of our approach, we set up simulated experiments to compare it with some of the existing works. We built 5 different scenarios, which contain static and dynamic obstacles in different density. Each of the scenarios were set in a square field with sides of 20 meters, and the quadrotor had to navigate through the obstacles to a goal point. Comparing to the existing approaches, our approach presents a better performance, especially in the scenarios with dynamic obstacles in high density. We also present real-world experiments to verify the effectiveness of our approach. We designed an experiment platform at the size of 165 millimeters. It weighs 960 grams with all the equipment like onboard computer and lidar, and its flight duration time could reach 6.5 minutes. In the first experiment, we test our system's ability of avoiding high-speed obstacles. We give the quadrotor a constant target position and let it hover, then throw soft balls towards it. We use motion capture system to record the velocity of the balls and the motion of the quadrotor. We also test the quadrotor's performance while continuously avoiding multiple high-speed obstacles. In this experiment, the quadrotor was able to avoid dynamic obstacle which is flying in the speed up to 6 meters per second. It is also able to handle the scenarios with multiple high-speed obstacles. The quadrotor is also able to avoid multiple balls while navigating at the speed of 2 meters per second. In the second experiment, we set up 4 different scenarios to verify the system's ability of navigating through dynamic cluttered environments. The first scenario contains static obstacles in different sizes and shapes in an empty test ground. We give the quadrotor a goal point and let it navigate through the obstacles. In the second scenario, we add more obstacles in the test ground to achieve higher obstacle density. The quadrotor is still able to navigate through the obstacles. In the third scenario, we let 3 pedestrians walk randomly in the test ground, and the quadrotor is able to take evasive maneuver when a pedestrian blocks its way. In the last scenario, we increase the complexity by let the pedestrians move some of the obstacles to block the quadrotor's way. The quadrotor is able to halt when the obstacle blocks its way, and then choose another way to bypass the obstacle. We have also tested the quadrotor's high-speed navigating ability. In this experiment, the quadrotor is able to reach the maximum speed of 6 meters per second, while flying through the obstacles in a low density.